Welcome to the SWAM course on analytical techniques. My name is Dr. Archana Singh and I shall be taking the tutorial on planar chromatography. Now, nothing in nature is really pure, and man through the ages has endeavored to separate substances into its purified parts or to observe the components of a mixture. So the objectives of this tutorial is to explain the principles of one of those techniques which has been used through decades and centuries for separation of substances. So the objectives of this class is to explain the principle of what we shall discuss as planar chromatography, the types of planar chromatography, the components of and the factors that affect the planar chromatographic process, and it will end with a brief discussion on the applications of planar chromatography. Now, broadly, you might be aware that chromatography is classified into planar, in which the stationary phase is solid particles or a thin liquid films such as those of silica and alumina gels that are coated on a solid support such as glass. The other type of chromatography is column chromatography, or a three-dimensional mode of chromatography in which the stationary phase is packed into a narrow column and the mobile phase is passed through the column using gravity or by applying pressure. Going into a very brief history, although modern chromatography or modern chromatographic methods owe its origin to the work done by Sweat, who was a Russian botanist, however, since ancient times, for example, by Pliny the Elder, there have been reports that substances impregnated with such things such as gall apple extracts have been used for identification of chemical substances. More recently, and the person in the picture is Runge, who was a German chemist employed as a manager in a chemical factory, and paper was used by Runge to differentiate between different color dyes. Of course, his purpose was not so much to develop the chromatographic process as to think of methods by which the quality control of these dyes that were being produced in the company could be ensured. So other than Sweat, who I just mentioned in my previous slide, there have been many pioneers in the development of planar chromatography, and in fact, the process continues to evolve. And as you would intuitively understand, the chromatographic process started with, as we said, very long ago experiments, maybe by Pliny the Elder, followed up for non-method development processes by Runge, but because of its inherent complexity and because of the evolution and the development of more and more materials that can be employed to improve the process of development of planar chromatography has gone on for more than centuries. And even now, we continue to find ways in which either the separation process or the development process or the quantification process can be improved in different ways. So some of the pioneers in its development were, as I previously mentioned, the Russian botanist Michael Sweat. Then there was Richard Willstatter, who published on paper chromatography. In fact, Sweat started his work with on columns. So he was using columns of calcium carbonate to separate colored pigments from plant extract. In terms of thin layer chromatography, which we shall discuss briefly, one of the pioneers was Ismailov, along with his colleague Schreiber, who published some of the first papers on plant extracts using thin layer chromatography. In fact, it was the papers by Ismailov and Schreiber, and not so much the work by Sweat, that gave the impetus to what we know currently as modern thin layer chromatography as a method with a variety of applications. Then Along with the process itself and the demonstration by Ismailov and Schreiber on the separation of these pigments, there were many labs that were simultaneously working on improving the process or struggling with different methodological issues related to the process. And one of these was Kirshner, who worked in the US Department of Agriculture, whose colleagues and whose fellow workers helped to develop what we now know as an indispensable part of the development of the thin layered chromatographic plate, the binders. So it was Kirshner's lab that started or did some pioneer work on binders for stationary phases to make that stationary phase more stable, the coating more stable so that it wouldn't drop off or it would not flake off with as the experiment proceeded. So the essential principle of what we know as chromatography. So the separation is basically because in a mixture of different analytes, each of those analytes would interact differentially with the stationary and the mobile phase. So in effect, what would happen is that a mass transfer would take place between the stationary and the mobile phase as the sample moves through the sample mixture, rather moves through the stationary phase carried by the mobile phase. And this partitioning between the stationary and mobile phase will result in the eventual separation of analytes between the stationary and mobile phase, and at some point each of these analytes would stop moving further, or if the separation has reached its limit. For example, if in a paper chromatographic process the mobile phase has reached the end of your paper, then the process is stopped and hopefully the separation has achieved its optimum state. So again, it basically means that the analytes which we see in the sample mixture travel different distances based on the strength of interaction with the stationary phase as compared to the mobile phase. And because of the different distances travel, which is an indication of the speed at which each of them would basically transfer between the two phases, because of these different distances, these analytes will then separate out. Now, as we briefly mentioned, that there are two types of chromatography. One is planar chromatography and the other is column chromatography. One is in effect two-dimensional experiment or a process. The other column is a three-dimensional process. Now, planar chromatography is divided into two types. One is paper chromatography, in fact, the simplest form with which scientists began to experiment. And then there is thin layer chromatography, as we said, in which there's a thin coating on a support which allows the separation to take place. Paper chromatography is essentially a qualitative analytical chemistry technique. In paper chromatography, basically, there is a uniform absorbent paper, which is effectively cellulose, which acts as the stationary phase and to some extent a support, along which or within which a suitable liquid solvent works as a mobile phase. Therefore, in this process, components of a mixture that are non-volatile, remember that most of these will be simple chemical compounds, these mixture components. These components of the mixture that are non-volatile can be separated and then visualized. Now, methods for visualization differ, understandably, based on the nature of the chemical compound that you're trying to separate. So, a simple schematic is shown in this slide, which is showing that paper chromatography essentially separates mixtures using a solvent, such as water, that carries a solute, such as ink, which is being illustrated in the schematic, up a strip of paper. And eventually, when the paper chromatography experiment is over, then from the point of application to the end of the strip of paper, you can see that the dye has separated into three different components that comprise the dye: the yellow, the red, and the blue. Okay? So paper chromatography is really a rapid, reproducible, and relatively inexpensive method to do some exploratory or qualitative analytical experiment, and often is also the method which is demonstrated for people or students who are starting out with understanding the chromatographic technique. Now again, a schematic diagram here which shows you an overview of the whole process. So the previous slide essentially showed that once the ink has been separated into the component colors, what it will look like. But a typical chromatographic setup for paper chromatography looks like this. The paper onto which the separation is to take place is first placed in a beaker with some amount of solvent. So typically, the amount of solvent is so that the base of your paper just dips into the solvent, but it will not wet the point at which the sample or the sample mixture is to be applied. So just the dipping solution level is just below the point of application, and typically a pencil line or a thin pencil line is drawn so that you are aware of where the sample is to be applied. Now, after placing the paper in this beaker with the solvent, which will act as the mobile phase, then the beaker is covered so that there is no leakage into the atmosphere, and for a while the beaker is allowed to be saturated with the vapors of the solvent. This allows a uniform movement of the mobile phase up the paper which is being used as the stationary phase. And after this saturation has taken place, typically about 15 to 30 minutes for a small separation for about maybe 2 to 3 inches of paper. After this beaker atmosphere is expected to have been saturated, then we apply the spot of mixture onto the pencil line, then wait for an hour or so. When we notice that the top of the paper, the solvent has reached the top of the paper, the mobile phase has reached the top of the paper, we stop the experiment and then begin the process of visualization. So we just had a demonstration, or we just had a look at what are the different components in a chromatography paper, planar chromatography experimental setup. Now let us have a look at the key elements in the paper chromatographic process itself. First, of course, is the type of paper, which could be filter paper, for example, a Wattmann filter paper of a certain strength, or even paper towels have been used for separation under some conditions. Then the element is the separation itself, which is of interest to the scientist, which involves the movement of analytes in a mixture. As we said earlier, this mixture is typically simple chemical compounds. It could be amino acids, lipids, and sugars, and this separation occurs typically by capillary action. The final and critical another element is the development or the visualization of the separated compound, which also gives you the semi-quantitative aspect of into this process. And different chemicals, understandably each of these chemical compounds is unique in nature chemically. Different chemicals are used for visualization of different types of chemical compounds that have been separated. So ninhydrin is very commonly used for amino acids, then ammonia for separating mixtures of metal ions such as cupric nitrate and ferric nitrate, for example. So in fact, at the same time or in the same paper that you've been used for separation of, say, metal ions, different visualization methods can be used simultaneously. To illustrate with an example, if, say, cupric nitrate and nickel nitrate and ferric nitrate are being separated, ammonia can be used to visualize the copper and the iron salts, whereas right after the visualization using ammonia vapors, some other compound like dimethyl glyoxime could be used to visualize the nickel compound. So simultaneously, multiple visualization methods can be used in the same separation template or the same paper in which different compounds have been separated. Coming now to thin layer chromatography. Now, thin layer chromatography typically involves what we call as chromatoplates. Now, chromatoplates are the plates on which chromatographic separation is taking place, hence the name. They could be made of glass, of metal, or plastic that are coated with a thin layer of solid absorbent material such as silica gel on which the separation will take place. Now, as we said, these plates could be made either of glass, they could be made of metal such as aluminium, or plastic. Now, each of these have their specific properties. So, glass expectedly will be brittle. A metal may have properties that make it more or less suitable for separation of certain compounds or for coating with certain stationary phases. And plastic can be convenient to use, but it may not always work under conditions in which either the separation is taking place or the conditions of development. Now, as far as these chromatoplates are concerned and the coating is concerned, sometimes plates incorporate a compound that will fluoresce under UV light. So remember, we listed the key components of a process, and the first one is, of course, the stationary phase, the second is the separation and the principle of separation, and the third is the development. So keeping in mind the properties of the compound that you're trying to separate, these plates can incorporate a compound that will fluoresce under UV light, and so your compound of interest, if it absorbs UV, can also be visualized. And typically for visualization, either short wave or long wave UV light is used. And one of the compounds that are used that will fluoresce under UV light is manganese activated zinc silicate. Now, the TLC method, as we said, the development began in the early part of the use of TLC began in the early part of the 20th century, and at that point in time it was mainly a qualitative method. So broadly it can be said that the thin layer chromatographic method is a qualitative analytical chromatography method used to separate non-volatile molecules, and it has quite a lot of sensitivity in its current form, and it is a fairly versatile technique. So a lot of applications ranging from separation of plant compounds, drugs, molecules, pesticides, a lot of applications are now available in which the TLC can be used. Now, broadly you can classify it as either being preparative or analytical, and in a classical preparative TLC, the separation and isolation of amounts up to 1 gram is available. Sometimes even under certain conditions, it could be even bigger. Now, a typical TLC method is not quantitative, but increasingly improvements in technology have enabled at least the high performance TLC methods that are available now to make it more and more quantitative. But typically, these are either qualitative preparative techniques or semi-quantitative results can be obtained by applying standards of known compounds in well-controlled spots. Now let's just elaborate upon what standards of known amounts of known compounds in well-controlled spots mean. Standards are substances that are similar like your compound of interest, except that they are available in a pure form and in known quantities. Now, a spot that is being applied along with your mixture, which contains these different compounds in different quantities, if a standard mixture of such a compound is applied in a well-controlled spot, meaning that the amount of spot which is being applied and going onto the chromatographic plate is well controlled and accurate, then a fairly quantitative estimate can be obtained through automated methods. And increasingly, many hyphenated techniques are being combined to make it even more quantitative. The other point about having a quantitative result is that automation improves both the accuracy and the reproducibility of the method. So, for example, for application of well-controlled spots, instead of manually applying these spots, it can be done by automated instrumental application. In some ways, of course, you can also say that TLC is an improvement over the original form of planar chromatography, which was done using blotting paper. And now the properties in TLC can be more tightly controlled because of the automation and the stringency of stationary phase preparation, as well as those of solvent transport.